Okay, we have seen that also in the analysis of variance or ANOVA of CRD with equal replication, but the continued portion of ANOVA from CRD with unequal replication is here started, and unequal replication of ANOVA is used when some data or some observation is missing from our experiment, in case from the lab, it might be from the laboratory or from the greenhouse trials. In such case, just we will use an ANOVA CRD with unequal replications. Therefore, here it is one example. The 20 rats were assigned at random among 4 experimental groups. Each group were fed a different diet. Unfortunately, one of the rats was died due to unknown reason. So one observation is missed from our experiment. In such case, just we need to conduct or use ANOVA of CRD with unequal replication. Here below are where the data of rat body weight in gram after being raised on these diets for 10 consecutive days. That means just the experimenter allowed the rat to feed or to eat what different diets for 10 days, and he measured their body weight, in order to compare the diet difference or the effect of different diets, that means on the body weight of the rat, that means. And then he got the data here. Here are what the treatments from feed 1, treatment 1, treatment 2, treatment 3, treatment 4, and treatment 5. The feed 2 similarly he recorded, but in the feed 3 treatment 5 were missed. Here there is no value of what the body weight. He doesn't measure, or he didn't measure the body weight of the rat, because of unknowingly the rat was died. So the dead thing is not or do not measured, because it doesn't have any value or meaning for our experiment or for this experiment. And in case of the forced feed, observations were recorded, and he then after he got these values, just it's better to calculate or estimate the treatment totals. In that means the feeds here are also, and the treatment totals were here are treatment 1, treatment 2, treatment 3, treatment 4. Sorry, these were the replications. Replication treatment 1, replication 1, replication 2, replication 3, replication 4, and replication 5. Therefore, this treatment and the third treatment, the fifth replication of this treatment were missed because of the rat was died, and recorded all the values, and then just calculate the totals, treatment total and the grand total is better. So the values were obtained. So the to estimate, the first one is estimating or calculating the correction factor, as we have seen in the previous slides, that correction factor is calculated by squaring the grand total and dividing it to the number of observations. So because of just we have 4 treatments and 5 replications, we may have 20 observations, but the one rat is missed. Due to this, our total number of observations could be 19. So just after we have squared the grand total, and we have to divide by 19, and then we'll have also this value of correction factor. The second step is estimating the total sum square values. That means TSS, and estimating, squaring all observations except the missed value, and summing up all observations in square value of all observations, and subtract correction factor from the summation of all observations, meaning that the first observation were 60.8, and square this value plus squaring the second observation 57.0 plus, and then lastly squaring the last observation in the fourth replication, the fourth treatment, the last replication. We can see that this here it is the fourth treatment with the last replication. Here the treatment, just we have two all observations, meaning this 1 2 3 4 5 6 and like up to 20. Then all those values shall be squared and sum up and subtract correction factor in order to get total sum square values. Therefore, based on this, then all the values could be squared and summed up, and then minus or subtracted 11 or correction factor, and the value obtained from this mathematical calculation is 4,354.70. So this one is what total sum square value. The third step is estimating treatment sum square value or treatment SS. In order to get this with no bias, with no missing data estimation, just we have to square all treatment totals and divide each treatment totals by its by replication. That means this treatment 1 or feed 1 was replicated 5 times, and the treatment first total could be divided by 5 plus the second treatment were also replicated 5 times, but in this case, due to one observation was missed, the number of replication were 4. Therefore, the third treatment total square value is divided by 4. We can see that here all observations were replicated 5 times, but this one is replicated 4 times. That is why we divide the sum square, the sum value of the treatment total value, squared value of treatment total 3 by 4. 1 2 3 4 replications, but all the other the treatments were replicated 5 times. And then subtract by correction correction factor, and then we'll have also this value. Then after we have got total sum square value and treatment sum square values, just we have to do error sum square values or ESS. And in order to get ESS, just we have to subtract treatment sum square value from total sum square value. So the total sum square value was this one, and the treatment sum square value was this one. So if we subtract this value from this value, we can get this much, or 128.75. Then the next step is calculating the mean square values or MS value, and the treatment MS is calculated as treatment sum square value divided by its degree of freedom or treatment degree of freedom, and the treatment sum square value was this one, and so this one divided by treatment degree of freedom by 3. That means number of treatments was 4 feed types minus 1. It gives us 3. So this value is divided by this one, and it will give us this much treatment mean square value. When we come to the error mean square values, just we have to divide the error sum square value by its error degree of freedom, and then we have error sum square values. From this we have got this here, this much value, and then divide this value by error degree of freedom by 15. That means in case of CRD, error degree of freedom is calculated as t into r minus 1, and by substituting all the values, the application of the treatment will give us 15, and if we divide this value with by 15, just we'll obtain also error sum square with the value of 8.56. Then after we have got all these values, just we need to go to calculate the FCAL, and treatment FCAL is calculated as the value of treatment mean square value or mean square divided by error mean square. Means just we have to divide this value by this value, and we'll have the value of 164.6. Then the next step is this finding the tabular value of f at 5 and 1% level of significance respectively by using treatment degree of freedom in the horizontal axis, and also error degree of freedom in the vertical axis, or in the row and column way of, and we'll take the intersection point at each level of significant level, that means. And then just we have to calculate the CB value. Just we know that CB is calculated as under root of mean square value divided by grand mean and multiplied by 100, and it's expressed in percent. Therefore, grand mean, the total number of grand total was 431.2, and then the total treatment total or grand total over n. Grand mean is calculated as grand total over n. The n was 90 because one observation was missed, and then if we divide this grand total by number of observations, just will have this value. So this value is important to calculate CV, that is it is used as a denominator. Therefore, just if we calculate and just do this simple mathematics, just we'll have also the value of 12.95% of CV in this experiment. And then after we have got all the values in the ANOVA, just we have to submit all the values also. Yes, therefore the treatment was 4 minus 1. It will give us 3 degree of freedom for treatment, and also t into r minus 1 and minus 1. This is what considered because of one observation was missing. Therefore t is 4 into this one is 5, so 4 times 5, 20 minus 1, I mean 20 minus t minus, I mean t is what, 4 times 1 is 4, therefore 20 minus 4 is 60. I mean yeah, 60. Sorry, treatment, the number of treatments is 4, and the number of application was the number of application was 5, I think. Yeah, you can see 4 treatments, 1, 2, 3, 4, 5. Yeah, therefore 4 times 5, 20, minus 4 times 1, 4, 20 minus 4 is 60. Therefore 16 minus 1 is 50. Oh, we can calculate as total degree of freedom minus treatment degree of freedom. The total degree of freedom is 18 minus treatment degree of freedom 3. So in both cases we can get 15 similar value. That means so we can get in two ways, that means. And we have to also submit all the sum square values calculated in the previous steps, and also the mean square values also, and the calculated or computed F values. This one we have calculated here, this value, and also and tabular value at 5 and 1% level of significance. In order to check how we can obtain such values, yes, we have to go to the F distribution table. Just we have to use that here treatment degree of freedom is 3 and error degree of freedom is treatment degree of freedom 3 and error degree of freedom is 15. Look, we have to go 3 horizontally and 15 vertically. Then the intersecting point will be used as the tabular value for its respective level of significance. Therefore, here it is the F distribution table. First, we have to go at 1%. So it is the first. the 1% level. Therefore, vertically 15 and horizontally 3. So this is the treatment degree of freedom here 3, and downward is the error degree of freedom. So 15. Therefore 3 treatment degree of freedom 1, 2, 3. Therefore 15 and 33. The intersection point at 1% is 5.42 is what the value of at 1%. F tabular at 1%. Therefore 5.42 is what the tabular value at 1% and also at 5%. Similarly, we can find at 5% of F distribution. The table F distribution at 5% of significant level. Here are the treatment degree of freedom and error degree of freedom downward. Then 15, 1, 2, 3, 3.29, 3.9. Yeah, 3.9. Therefore, the values are correct and will match with the values which are found in the F distribution at 5 and 1% level of significance using the treatment degree of freedom as numerator and also error degree of freedom as denominator. Here also the CV value in percent is placed below the ANOVA. This is the principle, and the designation is two asterisks designated here indicates there is highly significant difference between the treatments because this value is greater than or larger than that of this value at 1%. That is why two asterisks are designated here. And because the calculated F value is greater than that of the value of tabular F value at 1%, and how CV could be higher, this is the big question asked here, because the 12.95% in the laboratory experiments is too much and large. Therefore, the question is how it could be higher. We know that in the laboratory and greenhouse conditions, the variations or the external source of variations also the rooms are homogeneous and no higher variability in the environment when conducting the experiment. Therefore, in such conditions and such experiments, the lower the CV is expected, and in case this indicates higher. That's why most of the literature said that or suggests that the CVs in such conditions or experiments conducted in the laboratory in the greenhouse is the CV value is expected to be less than 5%, but it's too much larger than that of 5%. Therefore, that's why the CV is higher. When I come to the conclusion, we can conclude from this ANOVA table, and the first one is there was highly significant difference, having two asterisks between that body weight treated with different diet in 10 days. That means there was 4 treatments, that means 4 different diets, and there was the body weight measured from the rat. Therefore, there is a highly significant difference between body weight treated with different diets, that means in 10 consecutive days. Therefore, but in this case, which treatment or which diet has the larger value and which diet has also the lower value? This information is not obtained as stated earlier in the ANOVA table. Rather, it tells us the presence and the absence of significant or not significant difference between the treatments. And also, when we see the CV value, the experiments showed the higher CV, and it indicates the lesser precision of the experiment, because as I told you, also in the case of in the case of experiments conducted in the homogeneous environments, the CVs shall be lower than that of 5. And also we can conclude as the hypothesis could be rejected because of the presence of significant difference, and the alternative hypothesis could be accepted. And to get new information from from this agricultural technologies and the course tutorials, the students and as well as other peoples who are interested to see and to get new informations, please subscribe this channel and like and share also, and also download also if you need it. And your comments are valuable and very important as far as it's constructive and also impressive. Therefore, I would like to say thank you.